Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD of this rectangle is equal to 4 units in its length. In addition, we know that inside this rectangle we have those two semicircles. The radius of this big semicircle is 2 units, the radius of this small semicircle is 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all those three angles inside rectangle ABCD are right angles. So I write it down. This angle is a right angle. This is also a right angle. This is a right angle. And this is a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle, this point P. Likewise, we will define the center of this small semicircle, this point is point Q. We will define the touching point of those two semicircles, this point is point S. We will define the point of tendency of tangent AE with this big semicircle, this point is point L. And finally, we will define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we will do a construction, that is to say, we will extend line segment AE inside DC of this rectangle by a straight line. Until they touch each other. Hopefully, this is their touching point. We will define their touching point. This point is point F. DC is one side of rectangle ABCD. So DC is one side of rectangle ABCD. It is absolutely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. When you extend a straight line by a straight line, the result must be a straight line. Therefore, DF must be a straight line. So if we focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees. According to rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the right small triangle ECF, we will define this angle EFC as alpha, and we will continue to focus on this small right triangle ECF. In this one, right angle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle, triangle ADF. On the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay, so here we have PD is the radius of this big semicircle, that is 2. PS is also the radius of the big semicircle, that is equal to 2 units instead. So I want to know PD equals to PS equals to 2, they are both the area of this big semicircle, that equals to 2 units. Likewise, QS equals to QC equals to 1, they are both the area of the small semicircle, that equals to 1 unit in its length. So QS equals to QC. And we have also here line segment CF. Line segment, we don't know the length of line segment CF, it is unknown. So we define the length of this line segment CF as X. So we have here the radius PL of this big semicircle, the radius PL equals to 2. So the radius PL is down to point L, that is the point of tendency of tangent AE with this big semicircle. So whenever you have a radius that is down to the point of tendency, like here, you can implement here rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB. This tangent AB is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have the radius OM that is equals to 1. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So can actually implement rule 1 in our drawing. Why? Because in our drawing, we have the radius PL that is on to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is on to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1, of course. Likewise, we have the radius QG of this small semicircle is down to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in this small right triangle GQF. This angle equals to alpha, this angle equals to 90 degrees, therefore this third recent angle must be equal to 90 degrees minus alpha. So the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle PLF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third recent angle must be equal to 90 degrees minus alpha. In the next step, we prove that the right big triangle LPF is similar to this small right triangle GQF. Repeat again, we prove that those two right triangles are similar to each other. So I write it down. We prove that the right big triangle LPF is similar to the right small triangle GQF. So why those two right angles are similar to each other? First of all, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF. In the big right triangle PF, and it is equal to this angle, that's actually angle QGF. The small right triangle FGQ. So I put again, I actually found out that angle PLF in the big right triangle PF equals to angle QGF in the small right triangle FGQ. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write now that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle QFG, it will be defined as angle GFQ. Then again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle LPF. In the big right triangle LFP, and it is equals to this angle, that's actually angle GQF, and small right triangle GFQ. it again. If we follow the angle LPF in the big right triangle, PLF equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees on the side, and therefore they are equal to each other. So if we prove that all the figures inside this big right triangle LPF are correspondingly equal to all the figures of this small right triangle GQF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle LPF is similar, this is the sign of similar, to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side LP in the big right triangle LPF over side GQ in the small right triangle GQF equals to side PF in the big right triangle LPF over side QF in the small right triangle GQF. I'll repeat again. We will derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of this big semicircle that equals to 2 units in its length over GQ. GQ is the radius of this small semicircle that is equals to 1 unit, and here it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. Again, PF in total equals to 4 plus x over QF. QF in total equals to 1 plus x. So if we found out that 2 equals to 4 plus x over 1 plus x. Here we multiply the equation by 1 plus x, and we get that two times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and we get that 2x minus x is x, so in total on this side of the equation we have x plus 2 equals to 4. Here we subtract 2 from this equation, and finally we get that x equals to 4 minus 2, that is 2. So we know that the length of line segment CF is equals to x is equals to 2 units. So I can know x equals to 2 units in its length. In the next step, we will prove that the big right triangle ADF is similar to this small right triangle ECF. So I write it down. We prove that the big right triangle ADF is similar with a small right triangle, triangle ECF. So why the big right triangle ADF is similar to this small right triangle, triangle ECF? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ADF. In the big right triangle ADF, and it is equal to this angle, that is actually angle ECF. In the small right triangle EFC. Okay, again, we actually found out that angle ADF in the big right triangle ADF equals to angle ECF. In the small right triangle ECF, they are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha. This is angle alpha, that is a common angle that belongs to both triangles. So we can find out that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it is belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to angle alpha, as it is belongs to the small right triangle, triangle ECF, it will be defined as angle EFC. So I'll repeat again. Actually, found out that this equation means that angle alpha equals to itself. We just put to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle DAF. In the big right triangle ADF, and it is equal to this angle. This is actually angle CEF. This one right triangle, triangle ECF. So I repeat again, I should have found out that angle DAF in the big right triangle ADF equals to angle CEF in the small right triangle ECF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we found out that all the figures inside this big right triangle ADF are correspondingly equal to all the figures in this small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that the big right triangle, triangle ADF, is similar. This is the sign of similar to the small right triangle, triangle ECF, according to angle similarity rule. And from the fact that this big right triangle ADF is similar to this small right triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AD in the big right triangle ADF over side EC in the small right triangle EFC equals to side DF in the big right triangle ADF over side over side CF in the small right triangle ECF. So repeat again. We will derive that side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. AD equals to 3 units in its length over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is 6 in total, and 6 plus 2 is 8. So DF in total equals to 8 over CF. CF equals to 2. So in total I should find out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so I write it down. So I should find out that 3 times 3 over EC equals to 4. Here we multiply this equation by EC and we get that 3 equals to 4 times EC. Here we divide this equation by 4 and finally get that the missing side EC is equals to 3 quarters or 0.75 units. But again, I should find out that this missing side EC equals to either 3 quarters or 0.75 units. So I write it down. EC equals to 0.75 units in its length. What is the length of side BC of rectangle ABCD? Actually, we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD equals to 3 units, therefore BC must be also equal to 3 units in its length. So I write it down. BC equals to 3 units in its length. So what is the length of the missing line segment? Line segment BE. From the drawing it is very easy to see that the BE equals to BC minus CC. Again, BE equals to BC minus CC. So I write it down. BE equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. We just like now found out that EC equals to 0.75. So in total, BE equals to 3 minus 0.75. That is actually 2.25 units. So if we found out that the recent 97 BE equals to 2.25 units in its length. Here we use the same rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC in total equals to 6 units itself. And the opposite side AB must be equal to DC. And therefore AB must be also equal to 6 units in itself. So already know. In the next step, we copy the right triangle ABE in a new page, and we implement the Pythagoras theorem on this right green triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. Again, side AB equals to 6 units in its length. Side B equals to 2.25 units. So actually, this is the right green triangle ABE that I copied from the original drawing. In this right triangle ABE, according to the Pythagoras theorem, AE squared, that is the square of the hypotenuse, must be equal to AB squared plus BE squared. So write it down. AE squared equals to AB squared plus BE squared. AE is the missing side, so we will leave it as it is. So AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36. Plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. So in total, we should find out that AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So if we found out that a squared equals to 41.0625, here we take out of this equation and finally get that the missing line segment AE is also the hypotenuse of this triangle ABE. AE equals to the square root of 41.0625. That actually equals to 6.408 units. And that is the answer to the question. So I repeat again, if we found out that the length of this missing line segment AE is equals to 6.408 units. Okay, so in the next step I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing we have rectangle ABCD. We know that side AD equals to 3 units in its length. In addition, we know that inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units, and the radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles in any rectangle are right angles. So those 4 angles are all right angles. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. Likewise, we define the touching point of those two semicircles, this point is point S. In addition, we also defined the point of tendency of tangent AE with this big semicircle, this point is point L. And finally, we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did the construction, that is to say, we extended side AE, or line segment AE, and side DC of this rectangle ABCD by a straight line until they touch each other. This is their touching point. We define their touching point, this point is point F. So here, DC is one side of rectangle ABCD. Again, DC is one side of rectangle ABCD. Therefore, it is absolutely a straight line. DC is the side of a rectangle. It is absolutely a straight line. Then we extended the straight line by the construction. We extended the straight line DC by straight line, and the result is DF. When we extend the straight line by straight line, the result must be a straight line. Therefore, DF must be a straight line. So if we focus on the upper side of this straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that said that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we focus on the small right triangle ECF. In the small right triangle ECF, we define this angle EFC as alpha. And then, the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, we focused on the big right triangle ADF. Beside this big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that said that the sum of the angles in any triangle is equal to 180 degrees. Okay, so here we know that PD equals to PS, the above the area of this semicircle is equals to 2, so each of them is equals to 2. Likewise, QS equals to QC equals to 1. They are both the area of this small semicircle that is equals to 1. CF is the unknown line segment, so we define the length of this line segment CF as x. So here we have the radius PL of this big semicircle. The radius PL that is equal to 2 is known to point L, that is the point of tendency or tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If A is perpendicular to GQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule 1. So inside the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees. And therefore this first angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. In the next step, we proved that the right big triangle LPF is similar to this right small triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the figures inside this big right triangle LPF are correspondingly equal to all the figures inside this small triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, I shall prove that the right big triangle LPF is similar to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side LP in the big right triangle LPF over side GQ of the small right triangle GQF equals to side PF in the big right triangle LPF over side QF the small right triangle GQF. Repeat again. We derive that side LP in the big triangle over side GQ of the small triangle equals to side PF in the big triangle or side QF in the small triangle. LP is the radius of the big semicircle, that is 2, over GQ. GQ is the radius of this small semicircle, that is 1. And it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4, plus x. So PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So from here I shall find out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And finally found out actually that 2 times 1 plus x equals to 4 plus x. Here we open the brackets here and we actually found out that 2 times 1 is 2. So it is 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation, so 2x minus x is x, so in total this side of the equation we have x plus 2, that is equal to 4. Here we subtracted 2 from this equation and finally found out that x equals to 4 minus 2, that is 2. So if we found out that the missing line segment CF that is equals to x is equals to 2 units. Okay, so in the next step we proved that this big right triangle ADF is similar to this small right triangle ACF. So write those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees, one is alpha, therefore they are equal to each other. So we should prove that all the three angles inside this big right triangle ADF are correspondingly equal to all the three angles inside this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, we should found out that the big right triangle ADF is similar to the small right triangle ECF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD in the big right triangle ADF or side EC in the small right triangle ECF equals to side DF in the big right triangle ADF or side CF in the small right triangle ECF. Repeat again, we can conclude that side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. AD is 3 over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6, and 6 plus 2 is 8. So DF in total equals to 8 over CF. CF equals to 2. So in conclusion, we should find out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so in total we found out that 3 over EC equals to 4. Here we multiply this equation by EC, and we found out that 3 equals to 4 times EC. Here we divided this equation by 4, and we found out that the missing side EC equals to either 3/4 or 0.75 units. And again we found out that this missing side EC equals to either 3/4 or 0.75 units in its length. So what is the length of side BC of rectangle ABCD? We have the rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. So here BC equals to 3. What is the length of this missing line segment BE? BE equals to BC minus EC. Again, BE equals to BC minus EC. So BE equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. Again, BE equals to 2.25 units. In the next step, we use the rule, the same rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC in total equals to 6, and the opposite side AB must be equal also to DC, that is actually 6. And therefore AB must be also equal to 6. In the next step, I copied this green right triangle ABE in the new page and implemented the Pythagoras theorem on this green right triangle ABE. Okay. This is the green right triangle ABE that I copied from the original drawing. Side AB equals to 6 units, side B equals to 2.25 units, and the hypotenuse AE is the missing side. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, and therefore, in this right triangle ABE, we get that AE square equals to AB square plus BE square. Again, AE square equals to AB square plus BE square according to the Pythagoras theorem. AE is the missing side, so we leave it as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in total, we shall find out that AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in total, we shall find out that AE squared equals to 41.0625. Here we took a lot out of this equation and finally found out that the missing 97 AE is equals to the square root of 41.0625. This is actually equals to 6.408 units. Repeat again, we shall find out that the missing 970 AE is equals to 6.408 units. Okay, thank you very much.